Hello and welcome to the official Quantemol YouTube page. Today's video is going to be a tutorial on how to design a chemistry from the ground up. The main idea is to demonstrate that the chemistry design is done step by step, adding reactions and complexity to the model gradually rather than just finding all the reactions possible and trying to run your model. In this tutorial we'll be using two examples, one with O2 and one with CF4. This is a two-part video and a PDF with all the information can be found in the description box below. To collect data for this tutorial, we used the Quantemol database QDB. The graphs were created using results obtained by the plasma modeling software QVT. So, the first step. Here we construct the most basic chemistry set necessary to get a stable simulation. The absolute minimum is the feed gas, electrons, and one type of ion. If the feed gas is ionized dissociatively, we need to add other neutrals. First example, A, oxygen. O2 as feed gas, electrons, and O2 plus as ion. Example B, CF4. CF4 as feed gas, electrons, CF3 positive as ion, F as a byproduct of dissociative ionization, CF3 as product of neutralization at walls. We should also not forget to include reactions at surfaces. A must is the neutralization of charged particles at surfaces. We let ions return as their neutral counterpart while electrons are fully absorbed. In the first approximation, we ignore effects such as secondary electron emission or the reflection of electrons at surfaces. The interaction of neutrals with surfaces is a bit trickier as it depends much more on the surface in general. Reactive neutral species can stick to walls and react with species sticking to walls. For our CF4 case, F, for example, can be absorbed by the wall and then form F2, which returns to the gas phase. On the other hand, the CFX radicals can form polymers at the wall. From these sites, F can return as CF4. The CFX radicals themselves can return as CFX plus 1 from fluorinated sites, but will simply stick to the polymerized sites. So which surface reaction dominates depends on the surface composition, which can also be different on different wall materials. This can be modeled by a surface site model, which is however beyond the scope of this tutorial. To demonstrate the effect of neutral losses at surfaces, we will let all neutral species except CF4 stick to the walls with a probability of 0.1 in the CF4 case and neglect it entirely in the O2 case. We test this basic chemistry in a simple ICP setup at 50 mTOR, varying the power from 100 to 1000 watts with our basic chemistry. Both gases, like typical electropositive gases, can be seen in figure 1. The electron density is a linear function of the power, whereas the electron temperature is essentially constant. Due to the dissociative ionization of CF4, we also have small amounts of F as a direct product of it and CF3 due to the recombination of CF3 positive. At surfaces, note how the neutral particles have much higher densities, 2 orders of magnitude than the ions, although they are produced by the same process. However, they are lost on a large time scale due to the smaller loss probability at surfaces and slower diffusion. Next, we will add neutral dissociation of the feed gas. After all, producing significant amounts of neutral radicals is the reason for plasmas in molecular gases. For the CF4, we first only add the CF4, making CF3 plus F pathway. For the O2, the dissociation into O. As figure 3 shows in the CF4 case, we are still in the regime of a rather small degree of dissociation. While the O2 is highly dissociated at the high end of our power range, note how the densities change linearly in CF4 case over the entire power range, while in O2, a saturation effect is observed. In figure 4, we do not observe a significant change in the electron density in case of O2. However, we do see a significant increase in the electron temperature as a function of power. This happens because the electron temperature self-consistently reaches a value where charged particles' losses and gains are balanced. As we do not have included the ionization of O yet, the electron temperature increases to counter the significant loss of O2 and therefore ionization channels. It is entirely possible to have a stable simulation producing species densities in agreement with experiments, although important ionization channels are missing. In this case, the electron temperature increases self-consistently to achieve larger ionization rates. Vice versa, if lost channels for charged species are missing, the electron temperature decreases. Keep in mind to not only rely on species densities, also check the electron temperature. If it is uncharacteristically high, you are likely missing important ionization channels, and if it is uncharacteristically low, you are likely missing lost channels. As the neutral dissociation fragments reach now significant densities, especially in the O2 case, we will now introduce the ionization of these species. We add the CF3 making CF3 positive and the O, which makes O positive channel respectively. As figure 5 shows, this leads to an increase in the electron density in both cases with a large effect in O2. Also note how the electron density now increases slightly faster than linear in the O2 case due to the significant change in the plasma composition. Furthermore, the electron temperature now remains constant. The effect on the neutral densities is negligible in the O2 case, whereas we see small decrease at a high power in the CF4 case. This is related to higher neutral temperatures. Another characteristic of molecular gas discharges is the presence of negative ions. We will add F negative and CF3 negative to our CF4 set and O negative to the O2 set. In the latter case, we will neglect O2 negative due to the expected low density. We will also deactivate the calculation of temperatures for all negative ions, as they are quite notorious for introducing instabilities in the sheared regions due to the combination of low densities and high electric fields. Apart from the production of negative ions via dissociative attachment, we will also include the ion-ion recombination for all possible negative ion-positive ion combinations. Please note, before adding any species to a chemistry, it is worthwhile to approximate the density analytically. Consider the mentioned O2 negative ions. They are produced by a three-body process, E plus O2 plus M, making O2 negative plus M. M is an arbitrary third body. Its presence is necessary to fulfill both conservation of momentum and energy. The rate of such processes is highly dependent on the pressure. In this case, it is a linear function of the third body density. Thus, we can express the particle balance for O2 negative, gains equal to losses, roughly as K at Ne NO2 Nm equal to K rec NO2 negative N ions. With the rate coefficients for K rec and K at for recombination and attachment respectively. For a rough approximation, we set Ne equal to N ion and NO2 equal to Nm, which yields as NO2 negative equal to Nm 2K at slash K rec. Typical values are K at equal to 10 to the power of negative 32 centimeters to the power of 6 per second, and K rec equal to 10 to the power of negative 7 centimeters to the power of 3 per second. With Nm equal to 10 to the power of 15 centimeters to the power of negative 3, at our conditions we get an estimated density of 10 to the power of 5 centimeters to the power of negative 3, which is negligible compared to the plasma density of about 10 to the power of 10 minus 10 to the power of 11 centimeters to the power of negative 3. It's important to note that in general the particle balance also includes diffusive losses, and in case of neutrals the production at the surfaces. In case of negative ions, diffusive losses can be neglected as they are trapped in the plasma bulk due to their large mass and the positive plasma potential. Here, figure 7 shows how both discharges transition from an electronegative to an electropositive plasma as a function of power. As we deplete the particles capable of producing negative ions, CF4 and O2, note how both densities deviate from the linear behavior as a function of power. The electron density increases slightly more than linear, whereas the negative ion density first increases less than linear and in the case of O2 reaches a maximum around halfway through our power range. Furthermore, the sum densities of electrons and negative ions are somewhat larger than the electron density in the previous case. This is a result of diffusion being slowed down by the heavy and rather cold negative ions. In terms of electron temperature, shown in figure 8, we do not see a large change in the O2 case, but a jump from about 3.5 eV to slightly over 4 eV in the CF4 case. The electron temperature is still almost constant, but this shows the opposite behavior than without negative ions on a small scale. It shows a small decrease instead of a small increase. This behavior is caused by the reduced electron density due to attachment. As the electron density increases, the electron temperature must increase to balance electron losses and gains. In the CF4 case, this has a substantial influence on the neutral densities. In figure 9, we observe an increase of roughly a factor of 2 despite the smaller electron density. This cannot be explained by a change in the gas temperature alone. Rather, the rate coefficient for the neutral dissociation of CF4 is very sensitive in the electron temperature range. Between 3 to 4 eV, this rate coefficient increases by a factor of about 5. Please note the behavior of molecular gases can drastically change at a different degree of dissociation. Usually they turn from being electronegative to electropositive, the higher the degree of dissociation. This can have a large impact on the dependence of species, densities, and other parameters as a function of power, pressure, etc. For example, the electron temperature is largely independent from the power in noble gas. In molecular gases, it can significantly change due to changes in the plasma composition and electronegativity, which in turn affects the rate coefficients and finally species densities. Do keep in mind to always check your chemistry for the entire range of plasma parameters that you want to investigate. After understanding the impact of the main electron process and different types of species, we will now fill the CF4 chemistry with the missing neutral species down to C and the accompanying positive ions. As reactions, we add the dissociation of 1F from the CFX molecule to the ionization channel to the positive ion counterpart and the dissociative attachment F negative where available. In O2, there are no additional dissociation products left. Excited states will be discussed later. As figure 10 shows, we see a significant difference in the negatively charged particle densities, despite the rather low degree of dissociation. Their sum is smaller and the transition to an electropositive discharge happens at a much higher power, 700 watts instead of 300 watts. A detailed explanation for this is beyond the scope of this tutorial. Likely candidates are additional dissociative attachment channels, CF3 and CF2, a reduced gas temperature, effectively increasing particle density and electronegativity, and additional electron energy loss channels by the newly introduced species.